we go. Okay, so review stuff. I'm going to try to record this so that everyone at home can see a review as well. But basically, as I think about this unit, I'm just thinking about this main idea right up here, right? That if I have forces that are unbalanced, then my object accelerates. We might say that in a bunch of different ways. Like, we might say that using some vocabulary. We might draw it using free body diagrams. We might picture it using velocity versus time graphs to like show what the acceleration looks like. Friction graphs are kind of their own thing. They kind of stand apart. They're kind of like a specialty subcategory in here. Or we could take that acceleration and deal with it mathematically. And even though there's a bunch of different ways you can picture these topics, what we're doing is looking at one main idea. So this is the map that I think you should have for your notes, because it puts the main idea of Newton's second law in the context of all the different pictures. Okay? So the main idea of this unit is that Newton's second law, that acceleration is caused by net forces acting on a mass. Now, you and I dealt with this in so many different ways. And what I'll tell you is there's probably 4 main that you're going to see pop up. Okay. So let's do the 4 main ones, right? And then I'll show you some special categories. So the 4 main problems that you're going to see on Thursday or Friday's test are all applications of Newton's second law, right? We could do this horizontally. That might be something like you're pushing a sofa to the right. Right? Friction acts backwards. But it doesn't overcome your force. And as a result, your force forward minus friction backward causes acceleration to the right. We've done a bunch of problems like that. So, easy problems, horizontal, forces cancel each other. That net force of applied minus friction acts on a mass to cause acceleration. But then we made it harder. We were like, wait, if instead of horizontal we make it vertical, then we have to deal with like elevators and apparent weight. And it's all the same problem, right? It's the net force is the force in the positive direction minus the negative direction. In an elevator, when like your elevator is crashing to the ground and the floor stops you. When the elevator crashes to the ground and the floor stops you, your apparent weight is very large because normal is greater than gravity. When normal is greater than gravity, your acceleration is positive, and you experience a feeling of like heaviness. Actually, you'd probably experience that heaviness as like overwhelming pain, because it would be like your own ribs are crushing your body. Good times. And that's because normal force, the other word for this, is apparent weight. How heavy you feel as a result of the floor pushing on you. And during like a massive elevator crash, the floor would push on you pretty hard, right? So we could do horizontal problems, vertical problems. I'm going to think friction is going to be its own special subcategory. And the reason I say this is because there's that special graph for friction. So you should be able to read this graph. You'll see like for the practice today that like you should be able to read the static and kinetic friction forces off. So if I gave you a problem and I labeled a static friction force of 8 newtons and you applied 10 newtons of force, that means your object will start moving. It'll start moving because you applied a larger applied force than the threshold of motion. And so I know my object will accelerate to the right. It'll accelerate in the positive direction. So a picture I might have for this is I might picture like more force to the right, to the left, such that your object is accelerating to the right. Cool, cool, cool. Which leaves the last one. I said there were four main. Right? The last type of problem was what we were doing on Wednesday and Friday for your class, this like ramp problem. And the special thing about a ramp is that a ramp still is going to have a net force, but that net force is going to be caused by a portion, like think a fraction of the gravitational force. So my picture for the ramp, I would show my ramp. My normal force is up and to the right. And I'm actually going to draw the components this time, just so that we can see they cancel. Gravity is going to have a y component that cancels out normal. That's FGY. And it's going to have FGX, cause acceleration. For ramp problems, we dealt with this mostly mathematically. I would expect like a math problem with ramps. If you were like looking at the homework and all the homework was pretty much math problems, it's probably going to be a math problem. Since the net force is just part of gravity, you get your gravitational force times the sine of the angle. But hey, open notes, nice thing is you'll be able to have those equations in front of you. And actually, I will give you all of them today. Whereas the normal force is equal to the y direction to get you mg cosine theta. So if I had to like overview in less than 10 minutes the entire unit, I would say these are the main categories. But let me show you like the little minor things so that you don't miss like, you don't want to miss small things. Those are worth points too, and they add up. Okay, minor things that are going to be assessed, but don't fit nicely into these categories or are kind of like related to these. In vertical motion, expect something about free fall, right? Free fall is just a special case of vertical motion. And in free fall, I have the easiest free body diagram ever. It's just one gravitational force. In free fall, it's just gravity. And important things you should know about free fall is that acceleration of 9.8 is the same for any object here. And the reason is, let's say I take my Newton's second law equation. Gravity is the only force. And if gravity is the only force, then the masses cancel out. And that means all objects fall at the same rate. In theory, all objects fall at 9.8 meters per second. So if I took like a wiffle ball and a softball, in theory, those should hit the ground at the same time. The only reason they don't is air resistance slows things down. So for free fall, this says gravity is the only force. I'm dividing it by mass to find the acceleration. The mass cancels out, so all objects accelerate at the same rate, even if they have different mass. So how about we could write something like mass doesn't matter, something along those lines. So all objects fall at the same rate because gravity is the only force speeding you up. Actually, on ramps, all objects accelerate at the same rate on a ramp because of the same thing, because gravity is the only force causing speeding up. Right. Two more little things you might see. You might see forces at an angle. You might see like pulling up on an object versus pushing down on an object. But I wouldn't like combine that with like elevators and ramps and friction. Right. A small thing you might see is 2D forces. So like if I pull up on an object, that makes its normal force smaller because the applied force has a y component that's going to partially cancel out the weight. This one is where I would want to use like sine going with y as opposed to sine going with x. Fay would pull upwards and partially cancel out gravity. So Fay pulls up, normal force pulls up, and those two together cancel out the weight of this object. But for 2D, you're probably not going to get a full mathematical problem. You should be able to answer things like conceptually, meaning that knowing that if you pull up, the normal force gets smaller. If you push down, that pushes the surfaces together harder. That makes the normal force bigger. And you should know that if the normal force changes, the friction force changes. But you're not going to have to full math out this problem. Right? I don't know if you remember the homework assignment. We only did one of these. And that's probably an indicator that you won't have to do that all mathematically. We'll save the math for the ramp problem. So we should do lots of things with forces. And I will take a picture of this so that it's like nice and easier to see. All right, and then I'll post that on Classroom for you. And where we started the unit then was saying like, once you have the acceleration, how does one picture that acceleration? And the way we would picture acceleration is actually using a velocity versus time graph. Right? We had this Michael Jordan free-falling problem. And a free-falling velocity versus time graph is going to be pretty obvious because every single second of time that passes, our poor Michael Jordan here is going faster and faster by 9.8. Right? It's a free fall problem because gravity is the only force acting on him until, the floor. All right, this graph is going to be an important one, but let's show you the more general velocity versus time graph. This graph is going to be important because it shows that free fall has a slope of 9.8. And if we wanted to figure out how far he fell, we could do that. In this case, I could figure out the slope. It goes 9.8 meters per second faster every second. So it would be 9.8 meters per second squared. And how far Michael Jordan fell? I would be doing area under the curve. In this case, I'd be using the area under the curve of a triangle. I use slope to get acceleration of a velocity versus time graph. And I use area under the curve to figure out how far he fell. In this case, he fell for 4 seconds. That's a base of 4. And at negative, I'm going to call that 40 just so that I can math this easier in my head. With a height of negative 40 meters per second. So he fell 80 meters and negative because he fell down. So this is a specific free fall graph. In general, and a bunch of people in my first period class were stuck on this. So just because it's been a while, I'll drop one last one out and then we're good. In general, with a velocity versus time graph, anytime you have a straight line, that indicates a constant speed. So let's say instead of Michael Jordan crashing in an elevator, let's say it's Usain Bolt sprinting. Right. Well, let's say he sprints at about 10 meters per second because he does. That's his approximate speed when he's running the 100-meter dash. He runs for 10 seconds. approximately. I know he's got a sub 10 100-meter dash. And then he takes like a few seconds to slow down. He would be going constant velocity to start with zero acceleration. And then acceleration is negative as he slows down. To calculate that slowing down acceleration, let's say he takes 10 seconds to 12 seconds to slow down. He would be going 10 meters per second slower in 2 seconds. So negative 5 meters per second squared. So I think all of the problems that you're going to see, I think you're going to get asked these 4 types of problems. 1 horizontal, 1 friction, 1 vertical, 1 ramp. One of them will have free fall in it. One of them is going to have some sort of velocity versus time graph in it. Ramps are probably going to be mathematical because we pretty much only dealt with them mathematically. And 2-dimensional is probably only going to be conceptual. So like, when does normal force get big or small? So with all of those things together, I think that's an overview of everything you need to know. What I'll do is I'll take pictures of the top board, this board, and that one. That way, if you miss something or it's on Zoom and it's like super duper small, you can go back and see it later. And I'll also put this recording onto Classroom later. So that way, like if it was hard to hear me, you can hear it better.